Neural Networks Explained. Simply Episode 3. AI Fundamentals. Explained Series. Hook, Context, and Recap. Welcome back to AI Fundamentals Explained. In our last episode, we discovered that machine learning isn't magic. It's pattern recognition powered by data and mathematics. We learned how algorithms find hidden relationships in data to make predictions about new information. Today, we're diving deeper into the engine that powers modern AI, neural networks. By the end of this video, you'll understand how artificial neurons work, why layers matter, and how these systems actually learn. This knowledge will help you grasp everything from image recognition to large language models. Section 1. What are neural networks? Let's start with the inspiration. Your brain contains roughly 86 billion neurons, each connected to thousands of others. When you see a dog, millions of neurons fire in complex patterns to help you recognize that's a dog, not a cat. In 1943, scientists Walter McCulloch and Walter Pitts asked a revolutionary question. What if we could simulate this process artificially? They created the first mathematical model of an artificial neuron. An artificial neuron is beautifully simple. It receives multiple inputs, each with a weight that determines importance. It adds these weighted inputs together, adds a bias term, then passes the result through an activation function to produce an output. Section 2. The building blocks. Think of weights as volume controls. If recognizing a dog, the furry texture input might have a high positive weight, while has wings would have a negative weight. The network learns by adjusting these weights. Bias is like a threshold adjustment. It shifts when the neuron decides to activate. Imagine you're deciding whether to bring an umbrella. The bias represents your natural tendency. Are you cautious or carefree about rain? Activation functions are crucial. The sigmoid function squashes outputs between 0 and 1. ReLU simply outputs the input if positive, 0 if negative. These functions introduce non-linearity, allowing networks to learn complex patterns. Section 3. Layers and Architecture. Real power comes from combining neurons into layers. The input layer receives raw data. Hidden layers transform this information. The output layer produces final predictions. Consider image recognition. The first hidden layer might detect edges and corners. The second layer combines these into shapes like circles and rectangles. The third layer recognizes complex features like eyes or wheels. The final layer decides, this is a car. When networks have many hidden layers, typically more than 3, we call it deep learning. GPT-3 has 96 layers. Each layer can learn increasingly abstract representations of the input data. Engagement bump. Section 4. The learning process. Here's where the magic happens. Initially, a neural network makes terrible predictions. Weights are random, outputs are nonsense, but it learns through a process called backpropagation. Backpropagation works like this. The network makes a prediction, compares it to the correct answer, calculates the error, then traces this error backward through every connection. Each weight gets adjusted slightly to reduce future errors. This uses an optimization technique called gradient descent. Imagine you're blindfolded on a mountainside, trying to reach the bottom. You feel the slope and take a step in the steepest downward direction. Repeat millions of times, and you'll eventually reach the valley, the optimal set of weights. Training happens in epochs. Each epoch, the network sees every example in the training data. Modern networks might train for hundreds of epochs on millions of examples. GPT-3 trained on 570 gigabytes of text data. Section 5. Real-world applications. Neural networks are everywhere. In healthcare, convolutional neural networks analyze medical images, often outperforming human radiologists at detecting certain cancers. Self-driving cars use multiple neural networks simultaneously. One network identifies objects, another predicts their movement, another plans the optimal path. These networks process sensor data in real time to make split-second decisions. Language translation relies on recurrent neural networks and transformers. These architectures can understand context across long sequences, enabling Google Translate to handle complex sentences with cultural nuances. Netflix's recommendation engine uses neural networks to analyze your viewing history, comparing it to millions of other users to predict what you'll enjoy next. This drives 80% of the content people watch on the platform. Section 6. Limitations and challenges. Neural networks have fascinating weaknesses. Adversarial examples can fool image recognition systems. A stop sign with carefully placed stickers might be classified as a speed limit sign. The black box problem is significant. We can see inputs and outputs, but understanding why a network made a specific decision is incredibly difficult. This creates challenges for high-stakes applications like medical diagnosis or criminal justice. Training large neural networks requires enormous computational resources. Training GPT-3 cost an estimated $12 million in compute time and consumed as much electricity as 126 homes use in a year. Conclusion. Word count: 1,650. Estimated duration: 11 minutes.